in Causal Inference and Statistics, that book right there. We're all the way down into chapter 3, and we're on question 3.5.1 right here. Okay, so here we're considering this DAG here, and we've seen this before throughout the chapter. And we're asked to do several things. All right. So the first thing we're asked to do is to find a C-specific effect of X on Y. Okay, so we want to know the effect of this guy right here, this X, on this Y, when C is set to some particular value. Okay, so we'll tackle that first, and then we'll look at the other questions here. Okay, so so when we are looking for, some, we're calling it C-specific here because we're looking at C, but I think in the book this is often called, just generally called, the Z-specific effect to imply any other variable that is not X or Y. We're looking for this expression right here. So we're looking for the probability that Y takes on whatever value, given that X equals some value, and the value of X is some function of C. All right. According to Rule 2 in the book, they call it Rule 2. It's on page 70 if you want to read a little bit more about it. But the rule states this, that the C-specific effect, probability of Y do X as a function of C, is identified whenever we can measure a set of variables, generically called S, such that S or the union of S and C, where C is not within S, satisfies the backdoor criterion. Moreover, the C-specific effect is given by this right here. Okay, so here's an expression for it, and here's another expression for it. Okay, so what does this mean? Okay, it means that we can identify the C-specific effect of X on Y so long as I can block all backdoor paths from X to Y with either some set of variables or, well, I shouldn't say or, the union of some set of variables or C. Okay, so in this particular case, notice that we can, well, let's look at the backdoor paths from X to Y. Okay, so we have some that go from, X, A, B, Z, Y, or Z, C, D, Y. Okay, I think that's it. So some of these paths are already blocked by C, right? Anytime that we come off of Z, then we're blocking, then C is blocking those backdoor paths. Okay, but we still have this backdoor path that goes from X, Z, Y. So in order to block all these paths, we need to block, we need to condition here on Z. Okay. Now, when we condition on Z, notice that we actually open up a collider between B, Z, C. So by condition on Z, we open up this path, X to B to Z to C to Y, but we're conditioning on C. Therefore, even though this collider is open, its path is impeded by C later. Okay. So our set, according to the rule, our set of non-C variables S only needs to include Z, right? So S equals Z here, according to the rule. Okay. So then our expression, okay. So this is just filling in. The appropriate variables into these spaces. If S equals Z, well then it's the sum over all values of Z for this expression right here times the probability that Z equals whatever it equals when C equals whatever it equals. Okay. Okay, so again, what is this expression saying? It is saying that when C takes on a particular value, what is the estimated effect of X on Y? Okay, so you probably don't want to lose track of what's being said with that expression. All right. So now, part 2 is we want to identify a set of 4 variables that need to be measured in order to estimate the Z specific effect of x on y. So no longer the c specific effect, but the z specific effect. And we need to find an expression for the size of that effect. Okay, so so now our expression looks like this. So previously we found this expression, right, where x was a function of c, and now it's just a function of z. And so let's go through the same exercise of trying to block all of the backdoor paths from x to y. All right. So so again, we have the same backdoor paths that could go from x to y, right? So the backdoor paths would be, x a b z y, x a b z c d y. All right. But we are using a z specific effect, meaning that we are sorry. The backdoor path that I just said, x a b z c, that's not a backdoor path, right? Because it's actually blocked by z. So, so the backdoor path is x, a, b, z, y. Okay. Now we're conditioning on z already. Okay. So we're going to condition on z. So, so we've blocked some of these backdoor paths. Okay. But again, by condition on z, we open up the collider from b to z to c, and down to y. So we need to additionally condition on something over here, either c or d, to block that path, okay? So, where are we at here? All right. So now our set of variables s, okay, is either c or d, okay? It can be either one or both. It doesn't matter. But we have to block those backdoor paths that we open by conditioning on z. So we can have two expressions here, right? We have this, or we have this. Again, this is just filling in. Just filling in the appropriate variables to the rule 2 here. Okay, that's all we're doing. All right. Now, finally, for part C, so we're going to use our answer from part B here. Okay, so we're going to use one of these answers. Okay, and I'm going to use this top answer, conditioning on C, to determine the expected value of y under a z-dependent strategy, where x is 0 when z is smaller or equal than 2. And x is set to 1 if z is larger than 2. Okay, and we're assuming that z can take on integer values from 1 to 5. Okay, so so I'm going to, like I said, I'm going to use this expression right here. Right, so I have the probability of y given that x is a function of z. Okay, so I have so I have this particular expression where I'm setting x equal to 0 whenever z is 1 or 2. Okay, so I'm summing over z equals 1 and 2, right? So, and when that happens, x equals 0. And then, if x equals 3 or above, greater than 2, oh, there's a mistake right there. I actually want x to equal 1 under this circumstance. Okay, so now when z is 3, 4, or 5, well, now I have that I'm setting x equal to 1. Okay. Now I could actually get an exact value of all of this if I understood what the probability distribution of z was, but we don't have that. We just say that we just know that it takes on values from 1 to 5, but we don't know the probability of it being any of those particular values here. Well, we would also have to know the conditional probability of x and y, but anyway, this is the expression for the z specific effect. No, how do I want to say it? This is the expression for the expected value of y given z when x is a function of z, and we've already discussed the function. Actually, I'm recognizing a little bit of an error here. This does not equal this. We want the expected value of y here, so I'm going to change that. Okay, there we go. Yep, so this is the expected value of y given x is a function of z. Okay, we'll call that good.